Welcome everyone to another live tutoring session in chemistry. Today we're going to be talking about the periodic table. There's a periodic table, there's a version that I prefer that's Sergeant Welch that has a lot of information in it. Then there's also a version that you may be given when you take a test, but many professors will let you have the Sergeant Welch version of the periodic table. It looks approximately something like this. So what we're going to do right now is the way the periodic table is laid out, it's laid out in a series of patterns. We're going to talk about some of those patterns in the periodic table, how you can use the periodic table to determine things such as the correct molecular formula, how to find the charge on a particular element, how to find what its valence series or its Lewis dot structure is, and then we'll go into quantum numbers, Vesper, and electronic and molecular geometries. Those last three we may not have time to cover today, so we'll be covering those on Thursday. But right now, let's go ahead and let's transition to some basic information here. Let's imagine that we have a periodic table here. We have our two columns over here. We have in between, we have down, we have another series of columns here. And then usually on your periodic table, you have a series that are down here. I'm not going to draw all this in other than to say that there are generally two columns here. There's one right there. This is hydrogen. And then you have this column. And then you have a column over here, column here. And then you have another series of columns. But the way the periodic table is laid out, it's laid out in atomic number. So hydrogen is labeled 1. Then over here, you have helium, that is 2. Then you would have lithium, that is 3. Beryllium, that is 4. Boron is 5. Carbon, 6. Nitrogen, 7. Oxygen is 8. Boron, carbon, nitrogen, oxygen. Let's see, I've missed one, so that's going to be fluorine and then neon. 1, 2, 3, 4, 5, 6. That's right. So these are labeled basically by their atomic number. And as the atomic number gets larger, it has more protons in it. It also has more neutrons. So our elements will get heavier as you move across the periodic table and down. But one thing that's common is that one last feature of the periodic table that I'm going to draw in, you have a dark stair-stepped line right here. This is your break point between metals and non-metals. It's a stair-stepped line. On this side of the periodic table, we have metals, with the exception of hydrogen. And on the other side of this stair-step line, you have non-metals. Now, elements that are in the same column behave very similarly. If you have a periodic table, one of the things you can look at is if you look at, say, I'm going to move my periodic table here, we have copper, silver, and gold. Notice they are all in a line right there. They are all in a line. They have very similar properties. That's also why we also use them for money, because they're very malleable, because they have very similar properties. One of the reasons they have very similar properties is their electron structure of their outermost shell. When you're putting elements together, it is the outermost shell of electrons that is going to determine how they react. And the term for the outermost shell of electrons, the outermost shell of electrons, is called the valence shell. So there are a couple of columns that have very specific names in here. This first column, with the exception of hydrogen, but everyone in that first column is called alkali metals. They are all called alkali metals. The second column also has a special name. Those are called the alkali earth metals. That would be beryllium, magnesium, calcium, strontium, barium, and so on down. When you get over to this side over here, this very last column with helium, nitrogen, argon, those are all called noble gases. Now, the reason they're called noble gases is that their outermost shell is filled with electrons, so they will not want to react with anyone else. That's one of the reasons when if you see neon signs, they put neon in a sign, one, because it's very easy to make it glow, two, if it gets out, it's not going to react with anything. You certainly wouldn't want to put fluorine in there. Fluorine was one of those things that if you think about 10, 15 years ago, you heard about CFCs, chlorofluorocarbons. The way a fluorine is designed is very reactive. So when that would get out, it would chew up the ozone, and that's why you had holes in the ozone that were appearing. So this column with noble gases is noble gases. They're called noble because nobles don't try and they don't combine with anyone else under normal circumstances. The last column that we're going to talk about that has a particular name is a column with fluorine, chlorine, and bromine. Those are called halogens. Something to know about halogens is that they are very reactive. But everyone on the periodic table is trying to get to have a noble gas configuration, like this last column here, that generally has 8 electrons in its outermost shell. So what happens, this is where we're going to talk about what the charge of each element is. Now, fluorine is only 1 away from neon, so it could kick off 7 electrons to get to be helium, or pick up 1 electron and become nitrogen's configuration. And so the typical charge, if it gets to do what it wants to do, I'm going to write the charges down here. I'm going to use these columns. So we have lithium, we have beryllium, we have boron, carbon, nitrogen, oxygen, fluorine, and then neon. The typical charge for these columns, this is going to be our charge here. Neon and everything in the noble gas will typically be 0. It does not want to react with anyone. Fluorine wants to pick up 1 electron because it's easier to pick up 1 electron than to drop 7. So fluorine is going to be -1. And most things in that column will be -1 if they have a choice. They can be other things depending on what's combined with them, but typically they're -1 if you're playing the odds in Vegas. When you get to oxygen, that column is typically -2 because it's easier to pick up 2 electrons. Remember that an electron has a negative charge, and so when these elements pick up an electron, they are becoming more negative. Nitrogen can be -3. And we're not going to make any comment about carbon because by the time you get to carbon, you can be -4 or +4. It's just as easy to pick up 4 electrons as it is to drop 4 electrons. Now, when we get over to lithium, you could pick up 7 electrons, but the easier thing for lithium to do is to drop 1 electron. And if it drops an electron, remember that neutral atoms, we may have talked about this last time, but neutral atoms our protons equal our electrons. So lithium drops 1 electron and becomes +1. Beryllium drops 1 electron and becomes +2. Boron drops 3 electrons and becomes +3. Aluminum, which is in the same column as boron, would behave the same way. So this is a general pattern that turns out, and that's true for these columns. Now, the section in here that we don't know, this section in here that is in between these two kind of towers on this side and this side of the periodic table, these are called the transition metals. I wish there was an easy way to tell you what all these are, but the fact of the matter, there really isn't. There are a few transition metals that have only one possible charge. There's zinc, which is a +2. You also have silver, which is a +1. And after that, it gets very helter-skelter. Most of these metals can have very many charges. But the important thing to appreciate is that metals are positive, nonmetals are typically negative. One last group to talk about our metals and our nonmetals is the ones that border right in here. This would be aluminum or silicon. This would be germanium and arsenic. We'd come down here, this will be tin and then antimony. These elements right along here that I am going to highlight, and I hope this shows up pretty well. Right along this stair-step line, they have a special name. They are called metalloids, which means they have some metal and some non-metal characteristics. Now, this may make some sense when you think about silicon. Silicon is a non-metal, yet we use it in our computers. It makes very nice computer chips. You can run an electrical circuit through, but it doesn't overheat like metals will when you run. If you run an electric current through a metal too much, it may heat. But silicon has some metal properties and some non-metal properties. Aluminum does not heat up as much as some of the other metals are. So a lot of wiring used to be made of copper is now made of aluminum. So silicon and aluminum are non-metal or metalloids because they border this stair-step line that you will see on your periodic table. I'm going to attach a short video that you can watch after this is over, and this will give you an idea about how the different metals all in one column will behave. I'm going to post it in the chat. You're welcome to copy it and watch it later. Ignore the music, but it is kind of interesting. And if you've ever heard the story of someone who's probably told the story about somebody in their high school once upon a time stole some sodium and it blew up on them, well, that may be true, but I've heard that story myself. But you will see what happens when students steal a piece of, or maybe borrowed a piece of sodium and tossed it into a lake. It's pretty impressive. But it gives you an idea of things in one column being very, very similar to each other. Now, the reason they are similar to each other is each line across, hydrogen and helium are all in one energy level. That is the first energy level. When you get to lithium, beryllium, boron, and all these, they are in the second energy level. There are only 2 electrons in the first energy level. There can be 8 electrons in the second, and then your third can have more, your fourth can have more. But each time you get to this end, you start again with a new series of electrons. So just to give you an idea, if we had helium, we would have helium with 2 electrons around it like this. And then if we got to lithium, what would happen is you would have 2 electrons in this first shell, but they don't really matter anymore because now there's another electron in the next shell. If we decided to draw neon, neon would have, well, actually not neon, let's do sodium. Sodium would still have its 2 in the first shell. It would then have 8 in its next shell. 1, 2, 3, 4, 5, 6, 7, 8. And then one more out here. Keep in mind that this is hydrogen. Hydrogen only has 1. So hydrogen has 1, lithium has 1, sodium has 1. It's one of the reasons they're all in our very first column. So you have probably not come to Lewis dot structures, but it's very much related to how the periodic table is laid out. So I'm going to give you an idea of Lewis dot structures, and these Lewis dot structures will be the same for everybody in that column. We have a column for hydrogen. Then I'm going to write, actually I'm not going to use hydrogen. I'm going to use lithium, but they will be the same. Only thing that will change will be the symbol. Here's my lithium. Here's my beryllium. Then I'll have boron, carbon, nitrogen, oxygen, fluorine, and then neon. And so if I was to draw lithium's dot structure, I would draw lithium, 1, and then I'd have one single dot outside lithium. And that would be my Lewis structure for lithium. We don't worry about the other ones that are inside. When you're drawing Lewis dot structures, you only worry about, only show valence electrons. And remember, your valence is your outermost electrons. When we draw beryllium, I would draw beryllium, and then I'd have 1, 2. I like to separate them. I think of electrons as people on a bus. I am not going to pair up my electrons until I have to. If you get onto a bus and there are other people sitting in seats on the bus and there's an empty seat where you don't have to sit next to anyone, you're usually going to go and sit next to that empty seat where you don't have to sit next to anyone. Electrons are the same way. Now boron would have 1, 2, 3. Carbon would have 1, 2, 3, 4. Nitrogen would have 5. So I'd start 1, 2, 3, 4. Now you have to sit next to that other person on the bus. Nitrogen has 5. Oxygen has 6. 1, 2, 3, 4. Sit next to the guy on the bus. Sit next to the guy on the bus. And then fluorine has 7, so that's 1, 2, 3, 4, 5, 6, 7. Our last one, neon, has 8. 1, 2, 3, 4, 5, 6, 7, 8. So now, number of electrons needed to fill. This column only wants to have 2 electrons to fill. Our second column only wants to have 4 electrons to fill. Our third column only wants to have 6 electrons in order to fill. It already has 3, it just needs another 3. Now we have where you are probably going to hear about the octet rule. You may not have heard it yet, but it says that in order to be completely happy, you want to have a full octet out here, which means this carbon wants to have 8 electrons, which means it needs 4. This nitrogen wants to have 8 electrons. The oxygen wants to have 8 electrons. The The fluorine wants to have 8 electrons, and the neon wants to have 8 electrons. Neon already has 8 electrons. So neon is complete. This can let you know how things will bond if everything is normal, under normal circumstances. So that is my caveat for this. I'm going to say under normal circumstances, hydrogen makes 1 bond. I'm going to say number of bonds. Hydrogen makes 1. Beryllium will make 2. Boron will make 3. Carbon will make 4. And then nitrogen will make 3. It can make 4, but it's generally going to make 3 under normal circumstances. Oxygen will make 2 bonds. Fluorine makes 1 bond, and under normal circumstances, noble gases make no bonds. Neon is certainly not going to make a noble bond, not going to make a bond. There are some elements that can violate this pattern, but they do not usually happen until you get to silicon or higher. Silicon or higher can go above 8 electrons and more than 4 bonds. The most common violators of that, here are the 3 most common violators of octet rule. Are going to be these 3: phosphorus, sulfur, and this may not make sense, but it's another part of the periodic table we're going to talk about if we get to today. The last one that is a violator of that is xenon. I know it's a noble gas, but it's so far down on the periodic table that it's so far removed from its nucleus that it can be very easy to plug off electrons and stick more on. So this is basics of Lewis dot structures. Let's talk about how we can find a balanced molecular equation or balanced molecular formula. Now, when we have a formula, I'm going to move to a new page. Let's talk about an element, or rather a compound that we are all familiar with. Let's talk about water, which is H2O. This means that you have 2 hydrogens and 1 oxygen. This is called a subscript. Getting a little ahead of myself. In a couple of weeks, when we talk about stoichiometry, subscripts are used to balance the actual compound. And we are going to balance it. They balance the compound and we are balancing it between positive and negative charges. Hydrogen is in that column where hydrogen is +1. When it combines with something else, it's +1. Oxygen is in the column where it is a -2. So you need 2 positive ones in order to get a negative. You have a positive, you have this is a +2, this is a -2, and the entire compound has no charge, so we just write it like that. H2O. So the charges will tell you what your subscripts are when you start to make formulas. Let's do, and here's another thing. I'm going to show you the one exception, but I'm just going to say with one exception. With one exception, the positive element is listed first. With one exception. You may see another one, but with one, I'll say one common exception. I'm just going to say one common exception. Now let's look at another one. We could have NaCl. We have NaCl because if you look at sodium, it is in the +1 column. You look at chlorine, it is in the -1 column. So you're done. There's nothing more need to be done. But if you had calcium, it would be written as CaCl2. Because calcium is +2, each chlorine is a -1, so you have to have 2 of them. So these positive and negative charges will balance. Here's another one. I'm going to show you, you have iron. And let's say that we have iron 2O3. Iron can be very many charges, but this is a case where this iron here was a +3, and my oxygen was a -2. So I had to say 2 times a +3, and then 3 times a -2. So your subscripts are used to balance these compounds. Now I want to show you a very common, this is our common exception. You're going to see this series. If you stick in chemistry, you're going to see a lot of it. It's the nitrogen-hydrogen series. This first one is called amine. If you've heard of amino acids, that's part of what makes it an amino acid. Then you have NH3, that's ammonia. And then we have NH4 plus. This is ammonium. This is a case where our -1 is written first. The nitrogen is a -3. Our hydrogen is the +1. So you can think of this as -3 plus 2 positives makes it a negative charge. -3 plus 3 positive ones gives it no charge. -3 plus 4 positive ones gives it a +1 charge. That's your very common exception that you'll see. You'll see a lot of things done with ammonia and ammonium. This is a weak base. This is a weak acid. You can use them to make a buffer, but that is something that we're going to talk about many weeks from now when we talk about acids and bases. So this is our charges. These are how our charges are laid out. Let's see, what else can we do? Let me show you this. You can be given a question asked about the charge. Now you can also think when you have charge, an almost synonymous term with charge is called oxidation number. Charge and oxidation number is the same. In about a week, if not sooner, you guys are going to start to see a series of polyatomic ions. Here's one of my favorites. It's PO4 -3. This means that this entire compound is linked together, and unlike a normal compound like water or salt or calcium chloride, it has a charge to it. This is called phosphate. in about a week when we talk about naming compounds, it's going to be one of the 10 that you're going to want to know. But one of the questions that typically is asked, they can ask you for what is the oxidation number on phosphorus in phosphate. So we are going to approach that as if it is an algebra question. We're going to say I have one phosphorus, I have one P, and then I have 4 oxygens, and they all yield a -3. Now, I know in all cases except for one, oxygen is a -2. The only one that I'll tell, and we'll finish that today with the only time you're going to see oxygen not as a -2. We'll finish with that today. But we're going to go with Vegas odds. The race isn't always to the swiftest or the strongest, but it's always the safest way to bet in Vegas. The safest way to bet on your numbers of your oxidation numbers in your periodic table is to go with what the general pattern is. So we're going to say that this is 4 times a -2. This gives us a -3. We now have phosphorus plus a -8 gives us a -3. Add your 8, add your 8, and the charge on your phosphorus is a +5. Right there. We can do the same thing with another very common polyatomic ion, also one that you're going to have to memorize, sulfate. We can say sulfur plus 4 oxygens gives us a -2. We don't know sulfur, that's the one we're looking for, but we do know the oxygen with one exception that I'm going to tell you in just a second. Is always a -2. This gives us an overall -2. Sulfur plus a negative, and this becomes a -8, gives you a -2. Add your 8, add your 8, and that tells you that sulfur's charge is a +6. So these charges, these subscripts, they're given down here, whether it's PO4 or whether it's CaCl2, and the charge that is written up here or not written at all, give you an idea about what the charges are in these compounds. I'm going to show you the one exception for oxygen not being a -2 charge, and that is something that you probably keep. You probably have it in your house right now, and that is H2O2. Now, H2O2 is what's called hydrogen peroxide. H2, and this is the only one that you should see, unless you see something else that is a peroxide. But this is hydrogen peroxide, and this is the one case we'll see oxygen as a -1. If you ever see peroxide in the name of anything, that also means that the oxygen is a -1. But in most cases, when it comes down to finding the charge, we deal with oxygen so much, and it's so plentiful, and it's so reactive that -2 is the safest way to bet on what its charge is. So let's do a quick review of what we talked about today. We talked about some of our very common noble families that are in columns, our alkali metals. And if you get a chance to watch that little clip that I sent you, it's pretty neat to watch the piece of sodium tossed into the water. The other thing that's kind of neat is to watch how much more reactive it is as you get down the table. Sodium and potassium are some of the most flammable things that you can keep in a high school chemistry lab. And even when you keep them in a high school chemistry lab, they have to be kept immersed in oil. And you need to check them pretty regularly, because if they're not immersed in oil, they're reactive enough that someplace like here, if you've been outside today, the humidity in the air will cause them to react and start to burn. That's also the reason why lithium is in that column. They'll show you how lithium burns. If you remember, I guess it's been about 10, 12 years ago, we had lithium hydride batteries. Some of them were catching fire. There's a reason why lithium makes a very good battery, but it's also not the most stable thing. You want to have a very good system and a very good containment on your battery. But that'll be interesting to see the Alkali Metals, that series, if you have time to watch it. The next column is our alkali earths. Then in that stretch between the two columns on either side, we have transition metals. Then over here, we have our stair-step line that separates metals from non-metals. Things that are along that stair-step line are called metalloids. We then have our halogens. That's the series right down the fluorine line. Fluorine, chlorine, bromide, bromine, iodide. Those series, those are very reactive. And then our last column are our noble gases. We talked about the charges of everyone. We talked about +1, +2, +3, because it's either to give up 3, 2, or 1 electrons than it is to gain 5, 6, or 7. Likewise, these gain electrons because it's easier to gain 1, 2, or 3 than it is to kick off 7, kick off 6, kick off 5. You can't make a comment or a generalization about this column with carbon, because that is going to be, it matters what else is with it. That's also, incidentally, anyone who studied any kind of science fiction, there was a series of stories many years ago, and there's probably still a few today, where they talked about the possibility of silicon-based life. And one of the reasons they picked silicon-based life, it's in the same column as carbon. It has the same setup, and the rigid setup of carbon is almost as rigid for silicon. But it's not quite as rigid, so it's a nice idea, but it has yet to be found, and it's probably just science fiction, at least as far as we can tell. We then talked about our Lewis dot structures, and that everybody in this column of lithium and hydrogen would have the same Lewis dot structure. And everyone in beryllium's column would have the same: boron, carbon, nitrogen, oxygen, fluorine, neon. This is also why, we'll talk about this in just a second, this is also why in hydrogen you generally only get 1 bond with hydrogen, 2 bonds with beryllium, 3 bonds with boron, 4 bonds with carbon, 3 bonds with nitrogen, 2 bonds with oxygen, 1 bond with fluorine, and no bonds in your final one. Silicon or higher can go above 8 electrons and have more than 4 bonds. Our most common ones that violate the octet rule are P, phosphorus, sulfur, and xenon. But that's something that we will talk about when we get there. That's just a little bit ahead of where we are right now. And last, we talked about how our charges tell us what our different values are, what our subscripts tell us what our different charges are, and how our molecular formula balances. Remember, we said that oxygen makes 2 bonds, that's why there's 2 hydrogens there. We said that nitrogen makes 3 bonds, that's why there's 3 hydrogens there when it's balanced. Chlorine makes 2 bonds, calcium makes 2 bonds, that's why there's 2 chlorines there. We could also talk about, this is very common. We have BH3, it's borohydride, and that would be because boron wants to have 3, that's why it's going to hook up with 3 hydrogens. We talked about our oxidation numbers and how to find our oxidation numbers, 2 of our very common polyatomic ions, and then we talked about our exceptions where our negative ones come first. We have hydrogen peroxide, which is the one exception that you should probably generally see. But any other thing that you see that's named peroxide would also be an oxygen that is -1. So that is sort of our introduction to the periodic table for today. On Thursday, we're going to talk about electron configuration, quantum numbers, Vesper theory, and what a electronic geometry and a molecular geometry is. That's going to be related to the Lewis dot structures that we had today. It is related, and these patterns are going to be similar across the board. So if you have something that is, say, NH3, you would also suspect that you could also have something that's pH3. Just like we have H2O, if you look on the table, we also have H2S. The pattern is the same all the way down. I hope this was helpful. Finding these structures and writing the basic molecular formulas is probably going to be something that if you're not doing it yet, you're going to be doing it in the next day or two. So you may find that helpful. And I will be here again on Thursday. We'll pick up again with a little bit of a review of what we did today, and then jump into molecular geometries and electronic geometries. Now, does anyone have any questions right now that I could help them with? So if no one has any questions, that's what we have for today. And I will be back on Thursday, and we'll talk about electronic geometries, molecular geometries, and quantum numbers. Quantum numbers sounds more complicated than it is. It's really not going to be that bad. So thank you very much, everyone, for being here today, and I will see you on Thursday.